So I'd just like to thank the conference organizers for putting on such a wonderful conference and for giving me the opportunity to talk about composable security. Pretty much everyone agrees that composable security is something important, but when I talk to people, most people don't really know exactly what it is. So that's what I'm going to try and get across to you today. What does it mean for a definition or protocol to be composable? So really, the one thing I'd like you to remember is a composable framework is a language which you can use to model cryptographic security. There are many different languages which are used in different areas of the crypto community. There are game-based security definitions. There are many ways of modeling security. And a composable framework is one kind of way of modeling security. Now, a security definition is then said to be composable if it is written using this language. That's kind of obvious. But there's another use of the word in the literature if the security definition is proven to be equivalent to a composable definition. For example, the trace distance criterion it's not explicitly written in a composable framework, but it's equivalent to a definition that you could write up using the composable framework. The problem with this other use of the word is that it's a bit ambiguous. We're not telling you what definition the trace distance criterion is equivalent to. There are many different ways you could model QKD in a composable framework, and there's one of these definitions which happens to be equivalent to the trace distance criterion, and we're not telling you which one, so it doesn't actually mean much. So I'm not going to use this in this talk. If a definition is equivalent to one in a composable framework, I'll say that. It's equivalent to, and then I'll say what definition is equivalent to. There's another misconception a lot about these composable frameworks. There's this generalized belief that you can only model very strong security definitions, and that is completely incorrect. You can also model extremely weak things, and I'm going to give you an example of the accessible information, how you can actually model this in a composable framework. So it would be an alternative security definition for QKD, which you can model in a composable framework, which is different and strictly weaker than the trace distance criterion. I'll come to that later during my talk. Now, the whole point of these composable frameworks and why they were developed and their main advantage of modeling security in this kind of language is that it allows us to model a complex system by looking at its parts. So you prove security for its parts, and then you can assemble all the parts together, and you get security, you get a statement for a whole complex system. Yeah. So I'm going to give you a brief, pretty long introduction. I'm going to have 80 minutes for everything. So an introduction about composable security and roughly the general ideas behind it, and then I'm just going to go through examples, because that's just show you a bunch of examples of how you use these languages to model QKD, how to model authentication and encryption. And right at the end, I'm going to model device-independent crypto. Now, the rest you can all find in the literature, except what I'm going to tell you about device-independent crypto. I'm basically going to take the existing security definitions, and I'm going to translate them into a composable language. So this kind of translation doesn't appear so far in the literature. It's something we've been wanting to write up, but it's not really a novel research result, because all you need to know is to understand device-independent crypto, and if you understand composable security, you can do the translation. So it's nothing really novel from a research point of view, but it's a new way of expressing the definitions, and I think it gives us a lot of insight into what device-independent crypto actually does. So let's start with some simple examples. Say Alice wants to send a message to Bob, and she has a key, and this is her message, and this is her protocol, which takes these two. So it's basically going to be some function which produces some cipher, the function of these two. So she generates this cipher, and she sends it to Bob, and you have Eve who intercepts it. Now, a very standard definition you'll find in the literature would be to say, well, we want Eve to get no information about the message given the cipher. So basically, the entropy of this should be the same as the entropy of that. I've decided to formalize it this way because that's rather common, and when in my undergrad studies I was taught about the one-time pad, I was told this is the security definition for the one-time pad. But there are other ways of formalizing it this. You can formalize it with games, where someone receives ciphers, and one cipher has to guess which message it corresponds to. So there are many ways of formalizing this in the literature. The basic idea that I want to capture here is the cipher gives us no information about the message. So this is a pretty good, pretty strong definition. Now, Eve might go and change the cipher and might send something else to Bob, some C prime instead of C. So when Bob does his decryption, he uses the same key as Alice, and he's going to get out some message M prime, and then he's going to get some value X, which is going to tell him whether he should accept this message or not. And what we want is we only want Bob to accept valid messages. So a good definition for authentication would be the following. We want a probability that Bob accepts a message which is different and that he accepts this should be smaller than epsilon. So these are very reasonable definitions which have been used a lot in the literature. And then when you want both, of course, you want both encryption and authentication, well, both criteria, and then we know Eve gets no information about the message, and Bob will only ever accept a good message. And all this looks really nice, and then suddenly people realized, wait, there's a problem with these definitions. So I'm going to show you a construction which has appeared in the literature. I think I have a reference on the next slide, where something can actually go wrong, or these definitions don't behave the way we'd expect them to behave. So we're going to split the key in two parts, K1 and K2. And we're going to use a family of hash functions. I'm not telling you what the definition is, just getting technical, and I don't want to get into the details, but it's the hash functions which are used for authentication. And to construct this example where something goes wrong, I'm going to introduce a function f, which takes one bit and produces 2 bits, and it works as follows. If f takes 0 as input, it's going to produce 2 zeros, and if it takes 1 as input, it's going to either produce 0, 1 or 1, 0, each with probability 1/2. And then fn would just be the concatenation of n times this function. So it takes a string n and it outputs a string 2n by doing this, applying f bitwise on every bit in the string. Okay, so now let's look at the encryption function. It starts as follows. We have our message. We're going to hash our message using this hash function and our key and append it to the message. That's the first step. This is the standard Wegman-Carter authentication. Then we're going to apply this function. So we're going to map our n-bit string, say this is n bits, into a 2 n-bit string. And then we're going to encrypt it using the one-time pad, using the second key. So now we have this cipher. And then on the other side, when Bob receives something, say he receives a C prime, he first has to undo the one-time pad, and then he gets some V prime. And then he's going to try and inverse this function. So each time he sees a 0, 0, he's going to map it to 0. If he sees a 0, 1 or 1, 0, he's going to map it to 1. And if Bob sees a 1, 1, well, he knows something went wrong because this is an invalid string, so he's going to reject it. So at the end, he either ends up with an n-bit string or some rejection symbol. And suppose he ended up with an n-bit string, he's going to now parse it in 2 parts, the message part and the tag part, and he's going to check if the tag corresponds to the hash of the message, the way it was constructed there. And if it is, then he's going to accept this message m prime, and if not, he's going to throw away m prime, and he's just going to say, okay, maybe an eavesdropper changed the message, I'm going to abort. So now if you look at this, I've written it up again here. The encryption is just the hashing, applying this function fn, the one-time pad. And it satisfies this definition. This is quite easy to see because we're just encrypting the one-time pad. This is uniform. Eve has no information about it, so Eve has no information about the message given the cipher. And it also satisfies this. This you'll have to believe me. I don't want to walk you through a proof, but it's very simple. It just depends on the properties of the universal, strongly universal hash function here. So this is also satisfied. But now Eve could do the following. Eve could decide that she's going to flip the 2 first bits of the cipher. So she does this. She sets C prime equals C and just XOR with this string, flips the 2 first bits. And now when Bob decrypts, the following thing is going to happen. If the first bit of M is 0, Bob is going to reject, and if the first bit is 1, Bob is going to accept. And the reason why this happens, it has to do with our function fn, which we have here. If the first bit was 0, this function fn maps it to a 0, 0. So when Eve flips the 2 first bits, it maps to a 1, 1. And when Bob tries to decrypt, well, a 1, 1 is invalid. You should never get a 1, 1, so it's going to reject. Whereas if the message started with a 1, it gets mapped to either 0, 1 or 1, 0. When Eve flips the 2 bits, the 0, 1 gets mapped to 1, 0 and 1, 0 to 0, 1. And then when Bob decrypts, well, he'll get the right message. So what actually happens is if Eve learns whether Bob accepts or rejects, she then learns the first bit of the message. And this is an unexpected behavior which was hidden for a long time and people didn't realize. And the first papers that I'm aware of, which pointed out were in 2000, 2001, these 2 papers, they study mostly the computational setting, but it's exactly the same thing happens. So there's a kind of problem with these definitions. It's not necessarily a problem. Maybe we're happy with that. Maybe we're happy with the fact that Eve could learn a bit of the message by seeing if Bob rejects or not. But certainly there's something unexpected, and we definitely want a stronger definition. So the first problem with this is that basically this happens. Eve can get this bit of information by learning if it was accepted or rejected. So we need a stronger security definition, and one way of finding the strongest security definition could be, for example, to use a composable framework, and we'd get a different definition. If we're trying to capture authentication and encryption, we would not end up with the definition which I showed you. But as I said, maybe we don't want a stronger definition, maybe we're happy with a weak definition. But there's still a problem with this weak definition, is that problem 1 is not actually apparent from the definition, and people went for many years using this without realizing that there's a problem. And if you use a composable framework and you try and capture a weaker definition which allows Eve to learn a bit of the message based on whether Bob accepts or rejects, you get a definition, you can model this in a composable framework, and you get something where it explicitly says, look, this is what Eve can do. Eve is allowed to make Bob accept or reject depending on the value of the message. So this sort of problem, which is hidden by the previous definitions, actually becomes apparent if you use a composable framework to try and model this weaker definition. The other example, which from the literature, which most people know, would be the quantum key distribution and the accessible information. So I'll also walk you through the accessible information and talk about the difference between the accessible information security definition and just the trace distance criterion. So if we look at a typical QKD protocol, Alice is going to generate some quantum states and send them to Bob. Eve might change them, and then they have this two-way authenticated channel they use after to discuss about the states and the measurements, etc. And at the end, they try and produce a key. And I'm going to call rho k E the final shared state of Alice and Eve at the end of the protocol. So the accessible information, which was security definition, is defined in this way. So we take this state, it's an information measure. We take this shared state and we measure the E path of the states using some measurements, and then you get a classical outcome, which is Z, and then you just take the mutual information between K and this Z. Take this mutual information and sort of maximize it over all possible measurements that Eve can do. So this is the definition of the accessible information, and this was used in QKD until about 2004. People just said the accessible information has to be close to 0. For example, Shaw and Preskill use it. Most of the papers during the 90s use something like this, some variation of this. And there's a problem with this definition, and I'm going to give you an exact setting where this problem becomes apparent. Suppose the key then is used as a one-time pad with a uniform message which has two parts, M1 and M2. And I'm going to suppose that Eve knows M2. So now, Alice and Bob run the QKD protocol, and they get their key, and then Alice encrypts this message using the key, and she gets the cipher. And Eve intercepts this cipher. So now let's look at the information Eve has. Well, she knows M2, that was our setting. She knows half of the message. And she gets this cipher, so she knows the cipher, and then she has her side information E from the QKD protocol. And if the message is uniform, you can show that this is actually equivalent to, so the information Eve would have about M1 is equivalent to the information Eve has about K1 given K2 and E. And now there's this interesting phenomenon called information locking, which was again only discovered after many years of using these kind of definitions. You can construct tripartite states, K1, K2, and E, where K1 and K2 are classical, in such a way that the accessible information of K1 given K2 and E is much higher than the accessible information of K1 and K2 given E. So proving that this is small doesn't mean that Eve is not going to learn anything about the message when this key is used in the one-time pad. So even though Eve has very little information about the key, we still can't use it. So like before, there are two problems with this. Problem 1, well, if part of the key is leaked, the other part may not be secure anymore. So here, part of the key was leaked because Eve knew part of the message that was encrypted. And we can use a composable framework to come up with a stronger definition. And if we do that, we'll come up to something which is equivalent to the trace distance criterion. But then the other problem is that this problem 1 is not apparent from the definition used. I mean, maybe we want a weaker definition in which this happens. Why not? And one thing I'm going to show you later is how to model the accessible information in a composable framework. And when you do that, it actually makes it apparent what the problem is. And you kind of have to model an Eve that doesn't have memory to be able to capture this in a composable framework. So these are just some little illustrations, kind of problems which can happen with security definitions when we aren't careful. And these are just historical examples where it took a long time for people to realize there's some ambiguity about these security definitions. So now let's move on to the composable frameworks. There are a huge amount of literature on composable frameworks. Here in blue, we have, I picked out what I consider some of the most important papers in just classical cryptography, proposing frameworks, proposing variations on the frameworks. Probably the most famous is Canetti's universal composability, but there are a bunch of other things which are more or less equivalent, and many variations of this first one. In the quantum case, there were three different variations which have been proposed, kind of generalizing this classical framework to the quantum case. And the one I'm going to be using in this talk to model all the examples is the abstract crypto framework, which was proposed by Maurer and Renner. And one of the main differences between this framework and all the others is that it doesn't really hard code any model into the framework, which is either classical or quantum. It tries to do things in the most abstract way possible, and then you can just apply this to classical cryptography or to quantum cryptography. So the standard approach, when you look at all the other frameworks here above, they all have the same approach. When you want to start modeling some setting, well, you start by some computational model. Some use circuits, some use Turing machines, some use input-output automata. They each have their own notion of how you're supposed to model computation. And once you've done computation, you have all these different entities that have to communicate with each other. So how do they communicate? Do they have tapes? They send messages? They have identities, etc. Once you have this, you can define notions of complexity. You can define how protocols are supposed to be executed. You can then define a notion of security, and when you've done all that, you can prove that your notion of security is composable. That security of different parts of a big system implies security of the whole. The abstract crypto framework starts on the other side. It tries to start with the most abstract structure possible, and right now there's a version which is unpublished, but is currently being rewritten, and they basically are using semi-lattices, so basically post sets with some extra structure and some homomorphism on this. So you have this sort of algebraic structure. And then they sort of instantiate this and say, OK, let's be a bit more precise. Let's pick out some structure with specific properties. And you get some kind of composable resource theory, just based on these abstract algebraic entities. And then you can start, you can have actually definitions of composition on this level, just on these algebraic structures. I'm actually going to show you an example where I'm composing recipes to come up with a recipe for making bread or sandwiches. So this kind of reasoning can really be applied to anything. It's just not necessarily cryptography. Then you can plug in abstract systems. So now you have systems which maybe communicate with each other. They have inputs, they have outputs. And then you can start being more precise about your system model. Are they classical inputs or outputs? Are they quantum inputs or outputs? How's the scheduling done? And then right at the end, you can maybe say, OK, well, my systems, I have some underlying computational model which will allow me to have notions of complexity or something like that. But a lot of the work we're actually doing is on higher levels which are completely independent of the computation model. So in particular, the composition theorems are proven on this level, and then you can sort of plug in anything you want. As long as it satisfies the axioms which are needed for the theorems to go through, you're fine. You can kind of interchange this part extremely easily, which is much more of a difficulty in this kind of framework, because here when you want to change something, you start have to prove everything, because the proof here depends on all that which is below, so you can't make changes without having to reprove everything. So in this talk, as I said, I'm going to be using the abstract crypto framework. I'm going to just consider the Alice, Bob, Eve setting. So for keeping things simple, we're always going to have an honest Alice, an honest Bob, and a dishonest Eve. The systems level, I'm not going to talk about it because it's technical and it's not actually relevant. But what I'm actually going to be using implicitly, there are going to be a bunch of drawings, and all these drawings are actually going to correspond to a mathematical object. And these objects have been defined in the literature. In particular, Gutowski and Watrous, they call them quantum strategies, and Kidibela and co-authors, they call them quantum combs. But this is a mathematical representation of the systems I'm going to be talking about. And in particular, all the examples I'm going to go through, you could obtain exactly the same security statements using, for example, quantum version of UC by Unruh. So I'm not going to give you any complex examples which change depending on the framework you use. It's just really all these simple Alice, Bob, Eve examples. Though there is one fundamental difference, is that the abstract crypto framework does everything in a finite setting, and all the other frameworks do everything asymptotically. So we'd have to sort of tweak these asymptotic frameworks to be able to get finite statements out of them. But apart from that, you'd get exactly the same results. There are a whole bunch of advanced topics that I'm not going to be talking about, at least not during the main part of the talk. If there are questions, I'd be happy to answer the questions. Nothing's going to be asymptotic in what I'm doing. I'm doing everything in the finite case, and you have to work a bit more if you want to make asymptotic statements. I'm not going to discuss the computational setting. Everything's just going to be information theoretic, just for simplicity. And then there are a whole bunch of complicated things. How do you model adaptive corruption, non-correlating dishonest players, etc. And this changes a bit from one framework to another. So there it gets a bit more complicated, and the framework you use becomes quite relevant for these complicated examples. So that's what the examples I'll treat. And the framework itself you don't get different security results. Yeah, in particular, things like messages with space-time locations or superposition of orders, it's something that we've actually done, and it's quite easy to do with well, in the sense that you just need to change your framework. You just need a model of systems that can capture this, and you plug it in the abstract crypto framework, and you suddenly have a composable framework that can model this. So let's do a bit of cooking. Say you want to make bread. You Google recipe for bread, pick out a recipe. Here are your ingredients you need, and here's a recipe, some kind of instruction saying what you do to get your bread. So you can actually see this recipe as some way of transforming these ingredients we're starting off with. So we have our yeast, our water, our salt, oil, flour, etc. And the recipe is instructions how to transform these to get some loaves of bread. Now, I would like to put pictures all over the place, but it gets a bit tedious working with pictures the whole time, and sometimes it's not precise enough, so I'm going to swap between pictures like this and some kind of notation where I'm actually using letters. So for example, there'll be a letter for each ingredient. Some usually use pi for protocols, which make this transformation, and some B for the bread that we get at the end. And these are just some kind of parallel composition saying I need all this in parallel. I need the yeast, I need the water, etc. So the recipe is going to say, okay, take some yeast, some water, etc. But it's not going to tell you the brand of yeast that you're going to use. It's not going to say if it's supposed to be tap water or bottled water, etc. So there's a lot of freedom when you look up the recipe. I can pick a very specific brand of yeast. I can pick up tap water, etc. And I'm going to get one kind of bread. And maybe I'm going to use a different kind of yeast, and I might get a different bread. In particular, if you start changing your flour, maybe it just says use flour. It doesn't say what kind. Use white flour, use whole grain flour. You're going to get something different. So when I talk about an ingredient, in fact, I always mean a set. It's kind of implicit. Some yeast is a set of possible yeasts that can be used, and you're going to get bread, etc. And at the same time, when I say you're going to get bread when you do this recipe, I'm not saying what the bread is going to be like. It's a whole bunch of sets of possible breads. So when I have this kind of notation, I'm saying, okay, if you use any of the foods which are acceptable by the recipe, and you apply the recipe, you're going to get something which is in this set of acceptable breads. So that's the kind of information you get from a recipe. And now when I start cooking, I usually have this problem that I'm usually missing a lot of ingredients. So I have to start somehow fixing it and replacing it with other ingredients. So suppose we don't have any oil, but you look in your fridge and you have a jar which has artichokes soaking in oil. So you could extract the artichokes and kind of use the oil from this jar. It might give a nice artichoke flavor to your bread. Say I don't have any yeast, so you start Googling what can you do to replace yeast, and then you find recipes which say, well, you can actually grow yeast. It takes 3 to 4 weeks, so you have to be a bit patient, but you can grow yeast with water, with flour, use grapes. There's actually naturally yeast in here, and then it's going to grow. A very long, complicated process, but you don't actually need to start off with yeast, so you can get yeast. So again, this would be some kind of recipe. You're transforming our artichokes in oil into the artichokes and the oil, so some kind of transformation between ingredients. And we have the water, the flour, and the grapes, and we transform it into yeast. So if I draw it here in pictures, this recipe says how to get oil out of the jar. Very simple, but you do it. And then we have our recipe says how to get yeast from these two things. And then we add a whole bunch of other ingredients. Now we have all our ingredients. Well, we can make our bread, and we get bread. And now maybe we want to make some sandwich with the bread. So the artichokes are still there. We just put them in the fridge. We don't do anything to them, so identity. And then we're going to make a sandwich with the bread and the artichokes, and then we get an artichoke sandwich. And then maybe this bread, we're going to keep it. So what we've done here, we've basically composed recipes. And if you put it all together, we have one big recipe which uses all these ingredients here and transforms them into this is the final state. So you can sort of think of some kind of composition of recipes to get one big recipe. So if you understand that, you pretty much understood composable security, because now I'm going to do exactly the same, but instead of cooking, we're going to do cryptography. So say we have an insecure quantum channel, some fiber optic, which is supposed to go from Alice to Bob. We don't necessarily know where it goes. There's maybe an Eve in the middle that is listening. And we have some authentic channel. So this would be a channel, this would be for the classical channel for doing QKD, channel between Alice and Bob, and we know that Eve cannot change the messages on the channel. And what we want to do is we want to produce keys. So I'm going to illustrate some long key here with 3 keys. And that's what the QKD protocol does. It starts off with these resources, and the protocol tells us how to use these resources, what we do with them, and how we transform them into these resources, which are some kind of long key. But now we have this authentic channel, where does it come from? Or, well, like when you're missing some kind of ingredient in the cooking, well, you can make it up. So to get an authentic channel, we can do it with an insecure classical channel, so something where Eve can intercept the messages and change the messages at will. And if you have a short key, that's something which is nice about authentication. You need a short key. In fact, it doesn't even have to be uniform for this to work. And our authentication protocol will transform these 2 resources into this one. So we can do that, and we get our authentic channel, and then we can run QKD. And now that we run QKD, well, we have some key, so we can start doing stuff with our key. We can maybe construct another authentic channel. And then, well, these keys, we keep them. And then we can maybe do the one-time pad, and given our authentic channel and our key, we're going to get some secure channel. And this key, we keep it. So when you start composing all these protocols together, what we've done here, we started off with nothing else than insecure channels, insecure classical channels, insecure quantum channels, and 1 short key. And we've done all these transformations, and we end up here with a secure channel, and we have key again, so we can start all over again. And so again, I'm just really assembling little pieces. Every little proof that I'm going to give for these little parts, it's like a little piece in a puzzle, and the proof comes with some definition of the interfaces, what this interface looks like, what this interface looks like. And if somebody else writes a paper with another protocol that has uses the same piece of the puzzle, you can take the 2, you can clip them together, and you get a new bigger piece. And there are other ways of going from these resources to some of the resources we construct here. For example, if you just go back a step to the authentic channel, there's going to be a talk in the 2nd session by Serge Fer, a paper by Louis Savary and Serge Fer, where they're constructing a secure authentic channel, which actually recycles keys, so you can get your key back. And they do it in a completely different way than QKD. You don't go through QKD, you go directly from here to here by doing authentication and recycling the key. Then there are going to be talks about authenticating quantum messages, which in fact do something very similar, but instead of having classical channels here, we're using quantum channels, and we're authenticating and encrypting quantum messages. We get a quantum secure channel with key recycling. So I'm going to give a talk about that, and there's another talk that's going to talk about that as well, also in the 2nd session. So there are many different ways you can sort of assemble different puzzle pieces and kind of get the same construction at the end. So now let's do QKD in a bit more detail. So I just told you we're doing this transformation on resources, so let's look at it. We need this in secure quantum channel. So basically, it's a channel going from Alice to Bob, and Alice puts something in, and Eve gets it, and then Eve can change it. Okay, that's. And we're going to need our 2-way authentic channel. So I'm kind of drawing it one way, because it's kind of a pain drawing it 2 ways. But the idea is Alice puts a message in, and Eve gets a copy of the message, because it's authentic. There's no notion of confidentiality. So Eve can get a copy. And then Eve can choose whether Bob is going to get it or not. So Eve gets some kind of switch here, she can flip, and then Bob is either going to get the message or some error symbol. Of course, in a completely asynchronous network, Eve could also choose not to do anything, and then Bob would not get anything, which I'm not drawing, but there's always a third possibility of nothing happening and everything freezing. So these boxes that I'm drawing here, with these little squared corners, you can actually, these are what you can model mathematically. Actually, have it here. This is what you can actually model these mathematically using these frameworks. So you can model them as CPTP maps between the inputs and the outputs. So these always correspond to something very precise. But I'm just going to stick to drawings throughout this talk. Now, these kind of systems, which are actually modeled here, you could make a set of all possible systems that we could consider, all possible systems that could be implemented, allowed by quantum mechanics. And when I'm talking about resources here, I'm talking about subsets of these, so sets of systems. And this is where the ingredients were important before. When I said the recipe says you use yeast, it doesn't say which brand of yeast you use. Here, when I say you need an authentic channel, I'm being extremely precise here. I've drawn one specific authentic channel, but you could imagine that there are maybe different ways that an authentic channel could be modeled. So whenever I have this notation with calligraphic letters here, these are my resources, and they're always sets of systems. Now, nearly all my examples are going to be sets with just one system inside, because that's the simplest. So you can think of it as a set with cardinality 1, where I've drawn very precisely here how the system works. But mathematically, we're just talking about sets of systems. So a resource is a set of systems the same way the ingredient in the recipe is a set of possible ingredients that could be used. And now when I draw some kind of box like this and another box next to it, I could, of course, put some bigger box around it, and I would get back another system of the same type. Again, has inputs, it again has outputs. You can again model it mathematically as some kind of map between the inputs and the outputs. So on these resources, I always have a notion of composition, which is defined, which says that if you take two resources and you sort of put them next to each other, you're going to get a new resource, which is again of the same type, which is again a set of systems. So these are the resources I start off with, and now we're going to construct a secret key. So what's a secret key resource? Well, ideally, we would love to have something like this. It's a box. Alice asks for her key, and she gets something back. Bob asks for a key, and he gets something, and K is chosen uniformly at random. That's really what we would like. But this is something which is too strong to achieve, because our protocol allows Eve to interrupt the communication, and then the players don't get a key. So we have to weaken it a bit. So the first natural way in weakening it would be, OK, if Alice requests a key, then Eve is going to get some kind of request saying, should the box output a key or not? And Eve can get to choose whether they get a key or not, and then they get the key. So Eve cannot choose the value of the key, and Eve gets no information about the value of the key. She just gets to choose whether they get a key or not. And this we can actually model if we make assumption that we have a strong authentic resource here where Eve cannot interrupt the communication. But since Eve can actually cut the communication on the authentic channel, she can do something which is kind of nasty. She can cut the last message. And if the last message is cut, one player is going to get the key, and the other player is not going to get the key, and they'll never know. And this is something which is very hard to avoid. It's kind of present in most protocols. So in fact, it's something slightly weaker where Eve actually has three choices. Either they both get a key, or let's say Bob doesn't get a key, or neither player gets a key. So this is actually the resource we're going to construct. Now, Eve could, of course, do something at her interface, because now we have three. When I showed you recipes, there's just one honest player cooking. As soon as we have dishonest players, well, Eve could also do something at her interface of this ingredient, and she could somehow change the ingredient in some way by doing something local, which is in front. Local objects, I'm always depicting them with round corners. So there's something which Eve does in her lab, and it kind of connects to these resources. So it'll only have two interfaces, one connecting to the resource and one basically connecting to Eve. So there's some kind of local operation, and Alice and Bob could also do local operations there. So Eve could do some local operations, and these kind of local things, we're going to call them converters. Just a technical term, because they are going to convert resources. It's like the recipes that transform ingredients into ingredients. Converters convert resources into other resources. So maybe Eve has, say, a set of operations we allow her to do. And when Eve does something here at her interface, if you put a big square around it, well, you're going to get just kind of, composing it or plugging it in, you're going to get a new, bigger resource, which again has three interfaces, and again can define it mathematically through the input and output behavior. So it's again going to be something of the same type. And now if we look at what kind of keys we're willing to accept as keys that we construct, well, I kind of had one here where we had this sort of simplified interface. But it's OK, it doesn't matter really what Eve does at her interface. Anything which is sort of K composed with something at Eve's interface, then you take the union over all things Eve could do, that's also an acceptable key. Because whatever Eve could do here, it can only weaken it for Eve. It kind of builds a stronger resource from the honest player's point of view, and it builds a weaker resource from Eve's point of view, because Eve is just getting to hide, wouldn't have any more direct access to this, only access through this converter. So our ideal resource we want to construct is a huge set of resources, which basically has anything like this. But this is, in fact, not enough, because here we still have some kind of perfect key which is perfectly uniform, and we're only going to construct something which is approximately uniform. So I need to introduce a notion of approximation, so some kind of notion of distance, so we can even talk about approximations. So now suppose that we have well, for that, we need some kind of metric on our system. So again, I'm using these quantum strategies and combs. So metrics have been proposed in the literature. There's the obvious metric, which is the distinguisher metric. So you take two systems R and S that have the same kind of interface, and you plug some kind of distinguisher in, and the distinguisher has to guess whether it's interacting with R or S. So it outputs a bit. And the advantage you have in guessing is sort of the difference between the probability of outputting 1 when you connect it to R or connect it to S. And then you take the supremum of all distinguishers that, say, all distinguishers allowed by quantum mechanics if we're just looking at the most general setting, or we could limit our set of distinguishers to those that have bounded memory. There are many kind of things you can do, but I'm just going to consider supremum over anything that's all possible distinguishers. So now that we have a metric on these systems, we can use it to define an epsilon ball around our resources. So remember, resource is a set of systems. So an epsilon ball, I'm going to use this notation, just put brackets around it with the little epsilon. It's the set of all systems which are epsilon close to something which is in R. Okay, put an epsilon ball around it. So now my acceptable keys that we can construct. So I define my ideal key resource, and then we don't care what Eve does at her interface. We take the union of all this, and we put an epsilon ball around. Now we get a huge set of systems, and this is some big resource, and this is what I am willing to construct. Okay, so now let's go back to our construction. I just started off with these resources. I said, okay, these are the resources they have. Now they're going to run a protocol. So protocol is something local they're going to do with their interface. So it's again with rounded corners for local things. Like Eve had a certain set of operations we would allow her to do. We might have a certain set of operations allowed for Alice and Bob. And this is basically the QKD instruction, saying generate these states, measure in this basis, pick bits at random, etc. So it's really Alice's part of the protocol, Bob's part of the protocol. So it starts off with some kind of, say, request that starts it all, and then they start their protocol, they send states, receive states, measure them, discuss it over the authentic channel, and then they're going to produce keys at the end. So yes, our protocol then is just a pair of the converters of the honest players. And now all this you can put together, you can sort of compose it, because our systems are composing this with that is just going to give a new system. So we get one big resource on this side. So now we want to argue, okay, what is done in the real world. So we want to argue that our protocol is constructing our key resource given these resources, which in English we could write it this way. The protocol constructs a secret key resource K from a two-way authentic channel and an insecure channel Q with error epsilon. So now what's the mathematical definition of this? The mathematical definition is going to be my real world is a subset of my ideal world. So the ideal world is everything which I said is acceptable. The real world is what actually happens, and I just want everything that actually happens to be acceptable. So this down here would be the mathematical definition of what I'm defining in this way as this resource transformation. So again, the protocol constructs this resource from these resources with error epsilon if the real world is a subset of the ideal world. Good. So now every composable framework comes with composable theorems. And this is really sort of the key part of the framework, which says that, well, this type of construction here can be composed. Because before I was drawing these puzzles, and it looked kind of obvious from the puzzles. You draw one piece, you draw another piece, you connect them, you get a new piece. But this is what you actually need to prove, and this is what the frameworks do. So suppose you have a protocol which constructs S from R, and you have another protocol which constructs T from S. What you want to do is prove that the composition of the two constructs T from R with an error which is the sum of the two. So basically, my real world now, I started off with R. You apply the protocol 1, which would then be the inner protocol, and then you apply the protocol 2. And the composition here is simply this. You take these two converters, you put another circle around, and you get a new converter. So now you want to show that if you plug this into R, you're going to get a subset of my ideal world, which uses T. So the theorem basically says if you have this and you have that, then you have that. Okay. So this was for composing my pieces of puzzle in this direction, and I of course had pieces of puzzle which I was putting next to each other like that. So you have another theorem which says if pi1 constructs S1 from R1 and pi2 constructs S2 from R2, then there's a notion of parallel composition of protocols which constructs S1 and S2 from R1 and R2. If you draw it, this was my first system here. Pi1 is plugged into R and pi2 is plugged into R2. And now I have the composition of the two into one big resource, the composition of the two into one big protocol, and the theorem which says if you have this, then you have that with the sum of the two. So this is these core theorems which are in the framework and which we just use to assemble all the pieces together. So a few comments about what I've done so far. I'm viewing cryptography as a resource theory. So protocols are transformations between resources. And this is completely unique to the abstract crypto framework. You would get the same security definitions as if you used UC for these simple examples, but it's really a completely novel way of phrasing it. And in fact, the framework is called abstract crypto, but it's also called constructive crypto. Kind of both names are used in the literature, and they highlight different aspects of the framework. So this is supposed to highlight this sort of resource theory aspect, and the abstract crypto highlights the top-down aspect of the framework. But you find both words in the literature. They're kind of used interchangeably. So we really view a protocol as a transformation between resources. So protocol constructs S from R. So we're really making constructive statements about protocols. At no point did I say a protocol is secure. I did not say QKD, I'm proving security of QKD. What we're doing is we're saying, OK, I know what QKD does. I know that QKD constructs this resource given that resource. So it's somehow saying, I understand what my protocol does. Now you can argue, well, maybe you've constructed a very silly ideal resource. That's possible. So the discussion is kind of split into two. One, saying, look, this is what my protocol does. It constructs this key resource. Two, is this key resource really the key resource we want? So the second discussion is the key resource, the one we want, would be sort of the discussion about security. If it's an absurd key resource that gives the key to the adversary, then we'd say, well, maybe it's not. We shouldn't use the word secure for that. But the framework itself is completely oblivious to how good or how bad our resources are. It just says, it's just really this transformation between resources. And composition of protocols follows trivially from this. So in the abstract crypto framework, these proofs of composition, they're really just a few lines, because they just rely on all this algebraic structure that you have, and it's actually quite simple once we've done really the job of writing it up as a resource theory. Another important comment here is that all the objects I've been drawing, all the boxes, they're all finite objects. And this is completely different from all the other frameworks. All the other frameworks look at sequences of objects. You have sequences of Turing machines, and then you're going to make asymptotic statements. In what I've done so far, I haven't shown you a single sequence. So if there's no sequence, terms like polynomial, negligible, efficient, they're just not defined. You can define them by taking sequence of statements if you want to recover these kind of things. But just what I've shown you so far, we can't actually use any of these terms. They're never going to require that the distance between the real and ideal system is negligible, because it's just not defined. We're just going to say it's smaller than some epsilon, and then if you want to argue that it's negligible, then you prove a sequence of statements, and you show how the sequence evolves with n, and then you can say, OK, this is negligible if that's what you want to do. If you're just interested in a finite statement, then you don't need to do this. So here, really, we're doing everything in a finite way. Now, so far, I've just said what QKD does in the case of some dishonest player that has access to this insecure channel and can modify the states. But this is not really sufficient. We also want to make a statement about what happens when there is no dishonest player. And this is really an important thing you find, of course, for every protocol in the literature. In QKD, it's called robustness. So the question is, what if we don't have an insecure channel with an Eve tampering it, but we just have natural noise? We still want to make a statement. We're going to get a key with high probability from that. So now this changes the resources in our real world. We're going to have an authentic channel where there's no Eve messing around with it, so there's no Eve. And instead of our insecure channel, we're going to have this noisy channel, which introduces some noise. So it's a fixed noise model. We understand our channels. We know what kind of noise to expect. And we're going to call this N. And now we're going to actually prove we want to make a stronger proof, because the other one we allowed Eve to decide whether we're going to get a key or not. But in the case where there's no Eve, we want to make the statement that we're going to get a key with high probability. So we're going to model our ideal key resource like this with no interface here, and it always outputs a key. So there are, in fact, always two statements we want to make. One is the security statement, where we're talking about what happens, the one I presented before. If there is an Eve, then we construct the weaker key k, where Eve could prevent the players from getting a key. And if you don't have this insecure channel, instead you have a noise and an authentic channel which can't be interrupted, then you get this stronger key, which is guaranteed to produce a key. So we really need sort of both statements for protocol to make sense, because this one is trivially satisfied by a protocol that always aborts. So this one guarantees that under good conditions we get a key. And now we tend to want this epsilon here to be very small, because we want our key to be very close to uniform, whereas the delta here we don't really care, it could actually be rather large. Maybe our protocol will only produce key with probability 1/2. That's fine. What is underline? I'm sorry? Underline. Oh, underline. I slightly changed the key resource. I've removed Eve's interface from here, and I removed it there too. If we have a channel which doesn't allow Eve to interrupt it here, and Eve can't change the messages here, we just have a standard noise, we actually get a stronger resource in which they're guaranteed to always get the key. Yeah. So now we have this statement in the literature which says the trace distance criterion is composable. So I'm going to explain what this sentence actually means. What the sentence means is if you have a protocol which satisfies the trace distance criterion, so I've just thrown it in here, it basically says the state of Alice and Eve, condition on accepting, should be close to something uniform, so the fully mixed state and Eve's state, then again weighted by a probability of actually terminating with a key. This should be smaller than some epsilon. So this is the trace distance criterion. And we need a second criterion which says that Alice and Bob should end up with the same keys. So the probability of them getting different keys is smaller than some correctness term. And you can actually prove that if these two statements are satisfied, then our protocol constructs our resource K out of these two authentic channels. You can actually also go the other way around. You can show that if this is satisfied, then we must satisfy these with slightly minor changes here. You have a little constant, but it's basically the same. So in some sense, you can think of these security definitions as being equivalent to these security definitions. So that's the reason why literature tends to say these are composable definitions, because they're equivalent to the, let's call it the obvious composable definition we actually want. It just gets confusing when people say it's composable without saying what it is equivalent to, because there are other ways we could formulate security. If we look at I'll sketch a proof for this. I'm sketching a proof for this because I'm actually going to be using simulators in the proof, and otherwise my simulators, I'm not talking about them during this talk. So let's go back. What I want to prove is that if this is satisfied, then this is satisfied. So it's a very simple proof. It's just a few lines, but I think it's a very, very instructive proof. So I'm starting from the end. I want to prove that this is satisfied. Okay, so my definition of this would be my real world is a subset of my ideal world. Real world is an ideal subset. Real world is a subset of the ideal world. It basically means because these are sets, for every element A in here, every element Q in here, there exists a K in here and a sigma in there, such that this is now close to that, according to this distinguisher metric. Now, I used sets where A, Q, and K just had cardinality 1, so it's kind of obvious what A, Q, and K are. So now the only sort of open thing we need if we want to prove this is find our element sigma, which is called a simulator in the literature. And the reason for it to be called a simulator is that most of the time it just simulates the protocol. That's the standard simulator. It doesn't always work, but most of the time you can get away with this. And in this particular case, if you plug in a system here that just simulates this, so it runs the protocol and all the information which is output, which Eve can intercept, is just output here. And at the end, it's either going to get a key or not, or it's going to get a key only for Alice but not for Bob. And then depending on whether it gets a key or not, it's going to flip the corresponding switches here, saying, OK, you can produce a key or you can't produce a key. So then the key which is output here is uniform and independent of the transcript here, except for the fact that it's produced only if this transcript allows a key to be produced. Another line, exactly. So here A, Q, and K, I'm just removing the quantifiers because this is a set with just one element. So we have to show that there exists a simulator, which will be this one, such that for all distinguishers. Now you can plug in a distinguisher around this box and distinguisher around this box and say, OK, I'm playing this game, I'm interacting with these systems, and I have to make a guess. And at the end of interacting with these systems, I'm going to end up with a state. I'm going to call row AB the state you get when interacting, row ABE the state when interacting with here, and row ABE tilde the state you get when interacting with here. So I'm going to have to find, this has to be smaller than epsilon. And now, by just massaging this all a little bit, we can show that if this, that we can now bound this by the trace distance criterion and the correctness, just using some triangle inequality and a few little tricks. And that basically finishes the proof. So that basically shows that if you have a bound on this, then you get a bound on this, then you get a bound on that. So this is why the definitions are equivalent and why people usually just directly use this. But this is really the meaning of these definitions. This is sort of the definition where the composable definition corresponds to. Now, the other statement which is found in the literature is that accessible information is not composable. So what this actually means is that if you have an accessible information which is close to 0 and your key is uniform, then this is not sufficient to get this kind of trace distance statement. And the way this is proven is by finding an example of a state that satisfies these criteria but doesn't satisfy that criteria. So that's simple enough. The problem with this kind of statement is that we're only saying what accessible information does not guarantee, which in some sense is a very weak statement. I'm saying, okay, this is what accessible information does not do, but I'm not telling you what it does do. And it still does something quite interesting. So let's model a weaker Eve. Let's model an Eve that doesn't have any quantum memory. Let's add another picture. Let's say that instead of the insecure channel, which is here, remember the way I modeled the insecure channel, Alice would put a quantum state in and Eve would get it out. And Eve would get the state and do what she wants to it. So let's explicitly model a weak Eve that doesn't have the choice of doing that. Her interface here is basically weaker. The only thing she can do is she can choose some kind of operation E here, which is going to map the quantum state Q to a bipartite state, Q and Z, where Z is classical and Q is quantum. And then Eve gets Z. And then the other Q there is sent on. So we're limiting Eve. We're saying, okay, Eve doesn't have any quantum memory. Eve can only do this kind of operation. Which, why not? I mean, there's lots of literature in the bounded storage model where Eve has bounded memory. Here I'm just saying Eve has no memory. We know the quantum memory is kind of unstable. Why not? This could be an interesting model to look at. Now what you can show is that if your accessible information criteria is satisfied, then if a protocol satisfies these criteria, then the protocol can construct our key K given these weaker resources. So given this weaker Q bar, instead of the Q they had before, I put a bar above. So this would be one construction which is achievable with this accessible information. The accessible information is in fact slightly stronger than this because it allows, if you want to get it exactly what the accessible information does, it allows Eve to have memory until after the authentication step, and then the memory of Eve should die before the keys are output here. But that was kind of a bit messy to model, so I just did the simpler case where Eve has no memory at all. So now if we compare these two statements I wrote up, one is the accessible definition, which now is kind of demonized in the literature of QKD. This is terrible, you shouldn't use it. And now I have something which is actually even weaker and which looks kind of reasonable. And here I'll say that one is bad and the other is good. And now when I say that something is bad and good, it has nothing to do with it being weak or strong. I don't care how strong your definitions are, how weak they are. You can make any assumption you want about the adversary. You can look at something as weak as possible. What is really bad about accessible information is that people used it for 12 years without understanding that they were making some kind of limitation on the adversary's memory. And that is the problem. If you want to look at something in a bounded storage model, you want to look at an Eve that doesn't have any memory, or Eve just has memory for a short period of time, all that is fine, it just has to be written out explicitly. And people were using a definition which they basically didn't understand. And that is really what's the problem with the accessible information. And we can actually do the same with this authentic and confidential constructions that I also showed you at the beginning. Suppose that we have a protocol which I put AE for authenticated encryption, which runs here using a secret key and using some insecure classical channel, and at the end we're going to output some message or some error symbol, and suppose it satisfies these two criteria. The natural question, like for the accessible information, what does the accessible information guarantee? You could ask the same question here. What does this guarantee? What do you get when you use these security definitions? And what you get is something which is very interesting. You get a channel, not quite sure what to call it. I call it like a Portmann channel here, which allows, Eve doesn't get, first thing, Eve doesn't get any information from the message, except maybe the message size, because you really can't hide the message size. But then Eve can decide if Bob is going to get the original message or is going to get some error symbol. And Eve can basically input, say, a set of messages, L, and if M is in this set, then Eve gets M, and if M is not in the set, then Eve doesn't get L. Then Eve doesn't get M. So Eve basically has the power to force Bob to get an abort conditioned on some value of the message, even though Eve never knows what the message is. And what you can show is that if these two definitions are satisfied by a protocol, then our protocol can constructs this channel and actually goes the other way. So if we compare the two kinds of definitions, we can think of these property-based criteria as being a partial description of this. We're saying, okay, message here, so the cipher which comes out supposed to be on this side gives us no information about the message, so it kind of explains a bit the relation between this interface and this interface. And the message that comes out here should with high probability, should basically be the same as this, or it should be an abort. So it basically defines the relation between this interface and this interface. But this, in some sense, is a partial description of what happens. We're not describing how Eve can actually influence this. And I'll again make the same statements that these are bad definitions because they're confusing definitions, because people make mistakes when they use them because they don't actually realize what is happening. And for quite a long time, now we tend to understand these definitions. But there's a long period in the literature where people started just defining protocols which satisfy the authentication definition, satisfy the encryption definition I showed you, and actually using them without actually realizing that Eve has this influence. So as long as you use this kind of notation, you're basically hiding the fact that this can happen. Whereas if you use this kind of notation, you're making it explicit. From a weak, strong point of view, they are completely equivalent. So again, it's nothing to do with it being too weak. I'm not saying we don't want this kind of construction. It's just that we're kind of hiding. We're just offering a partial description of what really happens. And here we're offering a complete, a total description of the resource which is constructing. We're saying, I know what my protocol does. It does this. That's the statement we're making. So if we go back to this authentication and encryption, we could then ask, well, how do we construct something which is stronger, something where the adversary doesn't get to choose an abort, that can't force an abort on Bob's side condition on the message? So we can do it in two parts. First part, we do an authentication. So we run a protocol which takes the message, produces some kind of cipher. Typically, the cipher will just be the message concatenated with a hash. But it doesn't necessarily have to do that. And if you choose this as some strongly universal family of hash functions, it does what we expect. And when we run some kind of protocol like this, using just a key and an insecure channel, what we get is this authentic channel, which I was already using for QKD. So you can show that this security criteria is actually equivalent to making such a statement by constructing an authentic channel out of these resources. So in some sense, it's composable definition in the sense that it's equivalent to a composable definition. It would be equivalent to this one. And then the encryption, suppose now that we have our authentic channel, and now we're going to use something, for example, the one-time pad. So typically it could be the one-time pad where the cipher is just the XOR of the message and the key. And you do that, what you're going to get is a secure channel. So now Eve can't decide whether Bob gets an abort or not conditioned on the message. Eve can just choose whether Bob gets an abort or not. And this is a strictly stronger channel because Eve is strictly weaker. And you can also show that if this criteria is satisfied, then that means your protocol is constructing a secure channel from an authentic channel and the key. So again, it looks like it's a reasonable composable definition because it's equivalent to a composable definition. The problem is that when if I give you the composable definitions, then you know how to assemble them. Okay, I have this authentication protocol which constructs the authentic channel. I have the encryption protocol which uses the authentic channel. So there's only one way of putting the pieces together to get the secure channel. So the authentication would be the inner protocol and the encryption would be the outer protocol. So it basically means you do encrypt and authenticate. And the way I constructed the protocol before, which didn't behave the way we wanted, it was by swapping encryption and authentication. So even though this definition is equivalent to that, and this definition is equivalent to that, if I just give you these two definitions, this one and this one, it doesn't tell you how to compose the two protocols to get something stronger. If I give you these definitions, it tells you how to compose them. It says, okay, this is the order in which we compose them, and we're guaranteed to get a secure channel. So now let's look at what happens when we compose them in the other way. If you run an encryption protocol and now in an insecure channel, I before had an authentic channel here, and now I'm putting an insecure one, for example, again, the one-time pad. What you get is something, some kind of confidential channel where Eve doesn't get information about the message, but she can change the message and maybe apply some function to it. For example, if you're doing this with the one-time pad, Eve can do bit flips on the message. And you can again show that this criteria is equivalent to constructing this. If now you run an authentication protocol on this, so now you have this confidential channel where Eve can apply any function f, the result of running the authentication is like it's going to sort of reject all the functions which change the value. So it's only going to keep the functions which either map to M or map to, which map to M or produce something else which then gets mapped to an abort. And so what we actually get is this malleable channel I showed you before. So when we compose the two together in the other order, we get this malleable channel. So when we have to first authenticate, then encrypt. Of course, we can replace this by protocol which does something stronger than just authentication, and then you could actually construct a secure channel. So it doesn't mean you can't get a secure channel by doing things in this order. It's just the authentication property is not sufficient to get it. So let's move on to the last example, which is device-independent cryptography. So in a few words, what device-independent cryptography is, it's how to do cryptography without fully trusting the devices. I put fully there because there is a minimum amount of trust that you have to put into your devices. This is motivated mostly by discrepancies between ideal model and implementations. You think your system is behaving in a certain way and it behaves in another way. So can we have a security definition where we don't really completely trust how our quantum devices work? It still requires a trusted classical computer, but this is, worst case, you could always do all the classical stuff on paper or in your head. There's some kind of interesting difference between quantum cryptography and classical cryptography. You can always do classical cryptography ideally without any devices, and then constructing a device is someone else's problem. For the quantum case, you can't really do it without devices, so the two problems, at least from a philosophical point of view, they're kind of more linked together. You can't really do, there's no ideal, you can't come up, can't do quantum cryptography just with your brain. Anyway, there's still going to be some fundamental assumptions about how the untrusted devices work. So let's look at an example. Alice now has this device in her lab. It's this box. She bought it from someone. She maybe doesn't fully trust the person who bought it. So let's say she got it from Eve. Eve got to program it. So Eve got to put some state inside, and this state decides how the device is going to work. The way Alice uses it is she's going to send it bits, and she's going to get bits back from the device. She's going to do this multiple times, and she's going to get multiple bits from it. And here's our first fundamental assumption about the device. No information leaves the device other than from Alice's interface. We can weaken this slightly. I'm doing it a bit stronger than necessary, but the really important thing is there's no information going from the device back to Eve. So that's already one assumption we make about devices in this device-independent setting, because if there was some kind of wireless transmit in here that just sent to Eve the sequence of bits being input and output, it would be completely insecure. So just the fact that I draw this like this means I'm assuming the communication follows my arrows. So I'm assuming there's no other communication. So I'm already making a few assumptions about how the device works here. Bob is going to have a similar device in his lab, also programmed by Eve, and he's going to get to query send it bits, receive bits from it. And now we want to do QKD, so we're going to give Alice and Bob some two-way authentic channel they're going to use, and Alice and Bob each run their local protocol. So now Alice, the difference between the protocol here and the protocol used in QKD is that this converter here can only do classical stuff. I mean, the whole point is the players cannot do anything quantum, so everything which is quantum, we're shoving it into this resource, and the protocols now are entirely classical, but they can still generate random bits. Right. So what happens when you run this? So here the order in which things go. First, Eve gets to program the devices. Then Alice and Bob run their protocol, and Eve gets can see the transcript here. I think the newer device-independent papers, they weaken this. Eve can program it, or input some states, then she sees a bit of the transcript, then she can input more states, then she sees a bit more of the transcript. So there are certain relaxations in which order things go, depending on which paper you're looking at. So what we want to do with this is, again, construct a secret key. So again, the same secret key as before. And these would be the definitions used in the literature. So they basically, the device-independent community basically did some kind of copy-paste of these definitions which were introduced in the non-device-independent setting. And you can show that they are reasonable definitions in the sense that they construct exactly this. They're using these two devices, and using this two-way authentic channel, you construct the key K. Well, they might look reasonable. There's one issue with it, is that all my resources that I've been drawing up to now, they're always one-use resources. They always get consumed. You know, when you use your yeast in your recipe, you don't have any more yeast after. When you use your device, there's no more device. When you use a secret key, there's no more secret key. So this is actually a problem which is maybe someone who's not an expert in this kind of notation won't notice immediately, but if you write that down and show it to someone who knows the notation, they'll be like, okay, your device is gone. Now you can't use your device a second time. And this is exactly what happens with device-independent QKD. These resources are consumed, and the security definitions which are used, which are these, are not sufficient to reuse the devices. They've been some explicit attacks, like the memory attacks from Barrett, Colbeck, and Kent, which show that if you use devices a second time, it's going to leak information about the key from the first round. So there's an obvious solution to this. It's to make some extra device-dependent assumptions. For example, your memory gets wiped between each round, or you can things like that, which would be sufficient to get around it. But of course, we don't want to do this because we're just making, we're doing additional device-dependent assumptions, which we don't want. So can we do better? Can we reuse the devices? And for me, this is the big open question in device-independent crypto. It's been around for years. I consider this paper to be sort of the elephant in the room that most people kind of avoid talking about. But for me, it's one of the most fundamental papers in device-independent crypto, and still there's no good solution as to how to reuse the devices. So I can't tell you how to reuse the devices, but I can try and model what it would mean to reuse devices. So this is our one round of our protocol. And suppose we use the device a second time. That means that Eve, after the first round, players get a key. Eve is going to, say, input some more states, and then Alice and Bob are going to do more queries. But I'm not going to say what they're going to do it for. I don't want to specify the future rounds, just simply Alice and Bob can interact again with the devices later on. So this would be some kind of device which gets used more than once, and I'm not specifying how it gets used again. And ideally, what we would want would be to construct a secret key, given that, and to get back new devices. This is actually the way key recycling is modeled. So I'm giving another talk in the second session. I'm going to do key recycling, and this is basically the idea. If you want your key to get recycled, you need a key on this side, and then you're going to get a key back on this side, which is going to be independent from everything else which is done. So these would be new devices which are independent. Now I'm putting these devices in my ideal world. But what you can unfortunately show is that this is impossible. There is no protocol which is going to satisfy this, at least not in the naive way where these devices are as powerful as the devices that we had there. There have been propositions in the literature that hide all the leakage which comes through which come here on the transcript. But there's one bit which seems impossible to hide, is simply whether the device actually produced a key, whether the device agrees to produce a key or not in the second round. It could abort, and by aborting, it's going to leak some information about the key in the first round, and we don't seem to be able to hide the abort, because the abort is not a matter of information being sent here, it's really a matter of whether I produce a key or not, and that is always accessible to Eve. So there's no way we can actually get devices back which are as strong as the ones we started with. So the current state of the literature is basically, well, this definition is too strong. We can't satisfy it. And this one is too weak because we get to destroy our devices, which, of course, is completely absurd. So now, big open question, what constructive statement lies in between? So how do you actually model devices that you can get them back, but they're somehow weaker than the original ones, or you can maybe only use them in a specific context? So that's still a big open question. And then what protocols would actually satisfy it? So that was for QKD, and now we can do very similar things about randomness expansion. In randomness expansion, I've now removed Bob, so we just have Alice, and Alice has both devices in her lab, and Eve gets to program the devices. And now, unlike the previous protocol where I was assuming that Alice and Bob could still generate random bits, now randomness is some expensive resource. So there's a general rule of thumb when you're modeling things this way. Everything which is expensive, you have to model as a resource, and everything which is cheap, you can kind of hide in the converters. So as long as the players can do quantum operations, your converters can be quantum, but then you're doing device-independent stuff. Quantum stuff becomes expensive, you move it into the resource, and the converters are just classical. But for QKD, we were still assuming they could generate randomness locally, so the converters could still do randomness. Now I can't do randomness locally anymore because it's an expensive resource I'm trying to model, so we push it off into a resource. So we're going to assume we have this resource which generates randomness, and here I've chosen to do it with public randomness. We could also have another variant in which it's private randomness, just Alice gets it. So here the order in which messages are sent is vital, and it's not really apparent from the slides. But what happens is, first Eve gets to program the devices, then the randomness, Eve gets the copy of the randomness. If, of course, it goes the other way around, if Eve first has access to the randomness, she knows what randomness Alice is going to use, and the whole protocol is completely insecure. So here the order is really important. And now Alice is going to run a protocol which is not only classical, it's also completely deterministic. So it's basically a function of R and whatever you get out of this device, and it's going to be mapped to another string, which is either R prime or possibly an abort. And what we want to show is that we get some longer source of private randomness. So we want to show that the device-independent randomness expansion protocol constructs this private source of randomness, where Alice gets some R prime or some abort, and Eve gets to decide if she gets the abort or not. That's it, yeah. So we can again show that the definitions used in the literature are basically equivalent. This is what they do, but again, it's without getting the devices back. So again, devices are destroyed. But this is basically what this kind of definitions guarantees. Now here, as I said, I did it with a public source of randomness. So our protocol doesn't only transform a public source of randomness into a private source of randomness, and also it expands it from something which is short to something which is long. There are also other variations where the source of randomness is where this one is private. So if Eve gets a copy, the security breaks down. And another one which is easy to model in a composable framework would be randomness amplification. So now our source of randomness is not uniform. And in this case, don't seem to be two papers that actually use the same model. Every single paper uses a different model. They make different assumptions about the resources you have available. I'm going to briefly mention one which is going to be in the afternoon session, because I think it's one of the most interesting papers, which makes some of the most interesting assumptions in the randomness amplification setting. So our source of randomness is not uniform anymore, so you can think of it as some kind of beacon which produces bits, and it has a whole history of bits which have been produced, and Eve has access to the history and the correlations between these bits. So Eve gets some kind of classical side information about the randomness. So here again, the order is important. First, Eve gets this history. Then Eve gets to program the devices. And then more bits are produced, and Eve gets the copy of the bits. So these devices can, of course, only depend on the history. And then you run some kind of protocol, and at the end, same thing, we get a private source of randomness. There are other papers in the literature which do things a bit differently. As far as I know, there's only one other paper which assumes Eve gets side information and can program the devices depending on this side information. It's a paper by Shi and co-authors, where you have now quantum side information, and Eve gets to program the devices based on this quantum side information. All other papers, as far as I'm aware, in the literature always assume that somehow the side information is only obtained after Eve gets programmed to the device, so that there's always some kind of product form between the memory of the devices and the randomness used. But then the Shi paper, although it's quantum side information here, and there's a min-entropy bound randomness instead of Santavasirani, they need like a huge amount of devices. They can't do it with just two. They need a number which is polynomial in the length of the string, or I can't remember the exact parameters, but it's huge amounts of devices to compensate. So again, the definitions used in literature, they do exactly this, where the devices get destroyed. There are other device-independent protocols, device-independent delegated computation, for example, and those I actually have no idea how you'd model them in a composable framework. So just to conclude, the main points that I went through. So a constructive, so now the composable framework, at least the one I showed you, but other ones are kind of equivalent, we're making this constructive statement. We're seeing this protocol as this I'm constructing S out of R. We're saying what this protocol does. One effect, or what this kind of language forces you to do, it forces you to write out R and S. You can't write out such a definition without saying what is R and what is S. And this avoids a whole bunch of problems which come where people make assumptions and maybe don't even realize that they're making assumptions. Most of the problems that appear in the literature is because people just didn't realize they were making some assumptions. And this kind of language forces you to model the ideal system entirely, and it forces you to model the real system, and it forces you to write out exactly who's interacting with whom and when and why. For example, if you were to model accessible information, you'd be forced to model that Eve only has bounded memory. If you try to model this ideal channel constructed by the protocol I showed you, you'd be forced to show that the rejection can actually depend on the value of the message. And again, these devices, you're forced to model that they are only on the real side, not on the ideal side, which means they get used only once. So a whole bunch of things which sort of people didn't realize were happening, and then someone came out with another paper saying, hey, look, this is an assumption you're making. Maybe it's not actually the definition you want. It's much harder to do. You can still screw up when you use composable frameworks, but it's actually much harder to do it. And then composition follows for free from these kind of statements. Thank you.